We kind of been talking about this a little bit since the beginning of the chapter is what are our limitations in viewing things optically? What are the resolution differences and how can we know how tiny we can see when we're looking at a given object? So the ability for an optical system to distinguish between closely spaced objects. So here's two closely spaced objects. I think this is Pluto and its moon Charon. Is limited to the wave nature of the light. When waves pass through an opening, they tend to spread out on the other side of the opening. And that same thing happens anytime we observe something because we observe everything through some sort of an opening. Your eye has an iris. The microscope has a diameter of the lens. The telescope has a diameter of the lens. A camera has an aperture. There's everything goes through typically a circular aperture. And so when the light comes through that circular aperture, it starts to spread out, and we can get interference between the light from two sources that are pretty close to each other. So because of this diffraction, the images consist of bright and dark fringes, which we don't typically pick up with our eyes, but we can pick them up with instruments. And then, particularly with telescopes, atmospheric effects can have a distorting effect on images. To determine the limit of the smallest things we can see given a certain microscope or telescope and a given wavelength, we'll use Raleigh's criterion. Here we're going to say that if two sources are two distinct sources, that they are distinct as long as the first minimum doesn't overlap. And so those maxima and minimum are shown here. And so at Raleigh's limit, this first maxima out here overlaps the actual peak of the other one. And then we could say that is just resolved because you can see a little bit of spacing between the two. But when the central maxima themselves overlap, we can't see any difference and it looks like one object. To express the minimum that we can see in Raleigh's criteria, we're going to use this formula where A is the width of the slit. So this is more like a rectangular slit we talked about in like Young's double slit experiment, but just one. Then the theta minimum that we can see, and we want this to be a small number, right? So to make this number smaller, we got to make this number small and this number big. So we want to use a small wavelength and a large aperture. So as long as the object that we're viewing takes up more of our field of view than this theta min, and then we can see it, and we can see that there's two separate things. So you can see here that these two are pretty much just resolved, that they overlap, but they are just resolved. And here you can see the first maxima overlapping with the central maximum. Recently, last year in 2019, they imaged a black hole for the first time. So how is it so hard to image something that's so big? Well, any of these massive, massive black holes are really, really, really far away. So they don't take up much of our field of view. And so we need a huge telescope to be able to see that. And so they used a wavelength of 1.3 millimeters to view the black hole M87 in a galaxy that is not too far from the Milky Way. It is 55 million light years away, and it has a diameter of 38 billion kilometers. So what they did is they decided, well, okay, this is the smallest wavelength that we have telescopes for, so this number is really small. How do we make this number really big? Well, they used telescopes all over the planet Earth and photographed the black hole at exactly the same time. And so what they did was they compiled all of that data. And so the telescope size was the size of the diameter of the Earth, because we have telescopes in the far northern hemisphere, we have telescopes in the far southern hemisphere, and east and west. And so they figured out the perfect time where we could point as many telescopes in that direction at once, all at the same time, and compiled all that data. So sure, it has holes, but that's how we get as big of a telescope as possible. So this is the radius of the Earth. So we got a fuzzy picture. This is an artist's rendering of what the black hole might actually look like, but this is pretty impressive that we were able to get even somewhat of an image of the black hole in M87. I believe that project is now working on imaging the black hole at the center of the Milky Way, Sagittarius A star, but there's a lot of stuff in between us and it. so it's a little bit more challenging to image and won't probably get quite as nice of a picture. So most apertures that we use are actually circular. Telescopes are circular, microscopes are circular, eyes are circular. So we need to change the formula a little bit and add this 1.22 for a circular aperture. So here we can see another images of this is again barely resolved. So here the Firk's maxima is just past the central maximum. But here these two central maxima are too far overlapped that we can't really see either one. So I know these are pictures and simulations. How does this play out in real observations? Well, here's a picture of Charon and Pluto. Now this is one of the original pictures. I'm not sure what year this was taken, but you can see kind of a blob here that might make you think that there's something else there, but it's not real clear that the light from these two sources are just not far enough apart to be able to clearly resolve them. Whereas if we can get a different telescope, you can clearly say that this is Pluto and the moon Charon. Okay, so using this formula mathematically is here we're going to go to the Arecibo, Puerto Rico, has a 305-meter diameter bowl, and it's using frequencies at 300 megahertz. Notice that there's lambda there, so we need to convert that to lambda using the wave equation. Remember that is c is equal to f lambda. So we're going to use theta must be greater than or equal to, because we're looking at the minimum that they can see, 1.22 times c divided by f to give us lambda divided by that diameter, and that gives us 1.22 times 3 times 10 to the 8th meters per second divided by 300 times 10 to the 6 hertz, which was that number given in the problem, and all of that is divided by the diameter of our dish. Gives us basically 4 times 10 to the negative 3 radians, or 0.23 degrees. So not even 1 degree, about a quarter of a degree. And if something up in the heavens is separated by a quarter of a degree, we can see each one independently, which is pretty amazing.